Hello everyone, how's it going? My name is Dan the Tutor. In today's video, we're going to be looking at electric potential, also known as voltage. We're going to see how similar it is to another concept called electric fields, how it's also related to other things such as electric potential energy. And overall, this is one of the easier topics when it comes to physics too. So with that, let's get started with the equation. So the equation for electric potential looks like this. V, which stands for voltage or electric potential, it's the same thing, equals K Q over R. Or personally, instead of R, I like to put a D in the denominator because it stands for distance and I easily know what that means. R means the exact same thing, it's a distance. Now before we use this equation, I just want to say how similar it is to other equations that we've already seen this semester, such as the equation for the electric field, which I gave in a different video. For that, I said it was K absolute value of Q over distance squared. And the reason why we had the absolute value before is because we're going to figure out the direction of the electric field by hand. In other words, electric fields point away from positive charges and towards negative charges. But now with electric potential, I don't want to use absolute value because the charge, being positive or negative, is going to determine whether the electric potential is positive or negative. And so with that, let's look at an example and help clear some things up. So let's say I have a positive charge over here, 2 microcoulombs, and a negative charge over here, negative 5 microcoulombs. And what I would like to know is, if these charges are separated a distance of 20 centimeters, I would like to know what is the electric potential right here, halfway in between these two charges. In other words, if they're halfway, it means it's 10 centimeters on both sides. And so how would I find the potential for this problem? It's simple. First we have to use the equation for the positive charge here. Then we will add that answer to whatever we get for the negative charge. So for the first one, I'll say the voltage or electric potential is K times Q, which is the positive charge first, which is 2 times 10 to the minus 6, divided by the distance, 10 centimeters. We do have to convert that to meters. So 10 divided by 100 is just 0.1 meters. And we also know that K is a constant. The value is 9 times 10 to the 9th. And so then if I plug this in my calculator, I will get an answer of 180,000 volts, which is a pretty big answer, I'll admit, but perfectly fine with the numbers we're using. And now all I got to do is I have to add my answer to the negative charge. So for the negative charge, that voltage is going to be K, which is 9 times 10 to the 9th, times the charge. This one will be negative 5 times 10 to the minus 6. And I am going to keep it negative to get the right answer. And then divide by, it looks like it's the same distance, 0.1 meters away. So divide by 0.1. And when I plug this in my calculator, then I will get negative 450,000 volts. One thing you'll also notice as we're getting these answers, I'm not going to write X hat or Y hat or anything like that, because as it turns out, electric potential is a scalar, not a vector, which means that I don't care about X hat and Y hat. We don't have to worry about those components, which is nice. And so then I just have to add my two answers together, 180,000 minus 450,000, and this will give me a final answer of negative 270,000, and that's volts. And there's our answer for the first one. So you see, that wasn't so bad, which means now we have to look at a harder one. And before we look at this next one, I have to give another equation for voltage. This one relates voltage to the electric field. The equation is delta V, in other words the change in voltage, is equal to negative electric field times R, which again, since R is a distance, I just prefer to use D personally, but in your textbook you might see R. And so I would use this equation if ever I'm given the electric field or I'm trying to find it, and the problem also involves a change in voltage. And by the way, this negative sign here, for the most part, I'm going to tell you, don't worry about it, because most of the time we're going to be, again, figuring out that minus sign by hand. I'll explain why it's there in the example we do next, but overall I would say don't worry about it. So now let's just look at an example and we'll understand what's going on here. So first, I'm going to draw two plates of charge. This side is a plate of positive charge, and this side is a plate of negative charge. And one thing we know about this plate of charge is that because electric field lines point from positive to negative, it means that we're going to have electric field lines that point from left to right. Now, I'm going to give you the electric field. The electric field is 100 newtons per coulomb. And I'm also going to say that these plates are separated by a distance of 2 meters. And now my question is going to be, what is the difference in voltage between the plates? Okay, so here's the question. In other words, I'm solving for delta V. And so that means I'm going to be using this equation. Delta V equals negative E times D, where E is just 100, so negative 100, and the distance is 2, and it looks like the difference in voltage is negative 200 volts, which then begs the question, should the negative sign be there? And if so, what does it mean? First, I'll explain why it's there in the first place. So as we can see, the electric field here points from left to right. That makes sense. In other words, the electric field points in the positive direction. However, by definition, what does delta V mean? Delta V means V final minus V initial. If I look at the plates here, I would say this side is the final because the electric field lines point there, and this side is the initial, which means my voltage is going to be some negative number minus a positive number. And if you don't know what I mean, let me just make up numbers and then maybe you'll understand it. Let's say this side's 10 volts, this side's negative 10 volts. If I do final minus initial, it would be negative 10 minus positive 10, and I would get a negative answer for my voltage. In other words, it makes sense why the negative sign is here. However, for this problem, since I just wanted the difference in voltage wouldn't make sense if it's a negative. It would be like if you said the difference between my height and your height is negative 5 inches. Like, we just consider difference to be a positive number in terms of English language. So for that reason, positive 200 volts is the answer, even though we got a negative. And so basically what this means, back for the plate charges, if there's a difference of 200 volts, then that means this plate could be positive 100 volts and this side could be negative 100 volts. But since we don't know it's these values exactly, they don't have to be equal to each other. That means the left side could be positive 150 volts and the right side could be negative 50 volts. We really don't know exactly what the voltage is on both plates, but we do know that the difference must be 200 from the right side to the left side. And by the way, if I looked at another example, like let's say both plates were positive, but one plate was just more positive than the other, then one thing we could even say was if the difference is 200 volts, this side could be 300 volts and this side could be 100 volts for its potential. And that's perfectly fine too. So now let's just move on to one more example. For this one, I am going to have a ring of charges placed around a circle. Above, we are going to have a charge of just some variable, positive Q. We are going to have the exact same charge on the right side, also positive Q. On the right side, we are going to have a charge negative Q. And then below, we're going to have a charge negative Q. And what I would like to know is, I would like to know what is the potential at point P in the center if the radius of this circle is 10 meters. So in other words, we have one above, one below, one to the left, one to the right, and we want not the change in voltage. We don't want delta V. We just want V, which means we're using the first equation that we used today. So why don't you give the video a pause, try it on your own first, and then unpause it when you're ready to see the solution. Okay, and here's the solution. So first, you may be thinking, the position matters, like above, below, left, right, because it mattered for forces and it mattered for electric fields. However, as it turns out, it does not matter at all for voltage or electric potential. The only thing that matters is the charge and how far away we are. Let me explain what I mean. If I want to find the voltage from this charge right here, above, then the voltage is going to be K, Q over D, or you can call it R. And then K is 9 times 10 to the 9th. Q is just Q, we don't know what it is. And distance is 10. And that's it, we're done for the top one. Now if I do this one to the left, you're going to notice it's the exact same equation. It's another 9 times 10 to the 9th times charge Q divided by 10. So that's it for the top charge and then the left charge. Now for the right one and the bottom one, you notice it's only going to be slightly different because it's a negative charge. But if I want to find the voltage right here from that charge, I would just say the exact same equation, except the only thing that changes is that it's negative Q now in the numerator divided by 10. but everything else stays the same. And then if you think about it, it's going to be the exact same for the bottom, just the negative q. So that's 9 times 10 to the 9th negative q over 10. And once again, we're just going to add these 4 answers together. And so then what I would say is that, well, it looks like all 4 of these charges are just going to cancel each other. I mean, the positive cancels with the negative. This positive cancels with that negative. No matter what the charge is, you're just going to get a final answer of 0 volts. And that's the right answer for that one. By the way, if they didn't cancel at all, in other words, let's say just for a moment that these were all positive instead of negative, then what I would do is I'd first of all probably keep K the same. I would keep Q the same. Maybe I divide by 10, maybe I just call it D, whatever. But I'm just going to multiply this answer by 4 because there's 4 charges that are identical, same distance, and so the final answer would be 4kq over d. And of course, that would be if they wanted the answer in variables. If they wanted you to actually plug in numbers, you could plug in 9 times 10 to the 9th for k, and you could plug in 10 for d, but we still don't know what q is, so you'd have to write q. And that's how you'd solve the problem if it was 4 positive charges. And so that's going to do it for today. Hopefully you have a better idea now of how electric potential works. Thank you all for watching, and I'll see you in the next video. Take care, and bye-bye.